Welcome to the Digital Amateur Television Experimenters Night. This is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. Do you realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world? Also participate in the night by coming up to the Queen's Domain clubrooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind, doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7 OTC.
Okay, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. Justin, VK7 Tango Whiskey at the microphone. And I wish to acknowledge Tasmanian Aboriginal people as the traditional owners of the land upon which we present tonight, and pay my respects to elders past, present and emerging, for they hold the memories, the knowledge, the culture and the hopes of Aboriginal Tasmania. Now we have a huge program tonight. You'll notice if I do a quick change over here, there's a whole lot of props and quite a few other bits and pieces that we'll be showing you. But and it all came about by an interesting find in a drawer at my particular work. Now I won't go into that, but anyway, now what I'm wanting to actually show you is and I'll just go to is all about one of these. This is a PDP 1170 PDP 1170 and I'm actually not sure where this is. It was found in the front cover of this book, which is the book that I found at the in the back of a drawer at work. And this is a wonderful little book around learning how to program a PDP 11 computer. But before we get on to that, I just want to go through a little bit of history around the PDP 11 and just give you a bit of an idea about what a PDP 11 actually is, because there's a whole lot of history that goes with a PDP 11, and there are many people out there. And please, if you have had any exposure to a PDP 11 or even used a PDP 11, I know Phil Groom, VK7 ID, who may or may not be on the stream because he's up in Queensland, but I know he posted a picture on the Discord channel when I said what we were going to cover tonight, and it was a picture of a PDP 11 disk pack. And it was at Launceston College when he went through Launceston College. So there are many people who I suspect of my sort of era who had probably had some exposure to a PDP computer, a PDP 8, a 7 and 8, an 11, etc., etc. So I have no doubt there are many people out there. So please, if you're watching on the stream, and hello to Lionel, KJ70FH, David Bannister, and Andrew Elwell, who I know probably has had some exposure to PDPs, and also Ken from New Zealand. Hello from Hamilton in New Zealand, ZL4KD. So Ken Duffy, fantastic. So please let us know where you're coming in from. Please let us know. And if you have used a PDP-11, please let me know and relate your experience in the chat channel. So PDP-11s. If I head to here, Wikipedia has a wonderful, as it does with most subjects, I have to say, a wonderful expose of PDP-11s. And so PDP-11s are DEC, or the Digital Equipment Corporation. They ran from about 1970 through to the late 90s. There are many iterations of a PDP-11. It was originally, there was a PDP-4, actually. There was a PDP-4 that... And the interesting thing about the PDP-4 is it was an 18-bit machine. An 18-bit machine. So it wasn't a 16-bit machine, it was an 18-bit machine. It was an 18-bit machine. There was then the PDP-5, which was a 12-bit machine. And then the PDP-8, there was that was also a 12-bit machine. And there's a comment in here that there were 50,000 of those machines sold. So it was becoming a whole lot more popular. And then they came out with the PDP-11, which was still... They increased that to a 16-bit machine. Didn't quite go back to 18 bits. But it's a 16-bit machine, and there were over 600,000 of those different types of models sold of a PDP-11. So that particular picture that I showed, that's a PDP-11 70, and the numbers after the 11 talked about and indicated what options were included in the machine, the disks, etc., the memory, and all of that sort of thing. So now, PDP-11 40 was the most common model. It was released. First release was 1970, which is 54 years ago. 1970 to 1977 to 1997. Sorry, 97. And it was discontinued in 1997, so that's 27 years ago. It ran an operating system called Batch 11 or DOS 11, DSM 11. It ran IAS, POS, RTSE, RSX 11, RT 11, Ultrix 11, 7th edition Unix, Sys5R4 version 1, R1, 2 BSD, so Berkeley Systems. That was the other version, the other stream of Unix. So there was Sys5R4, Sys5, and the various revisions, and then there was BSD was the other stream. It's a 16-bit platform. It was succeeded by the VAX 11. Now, lots of people probably had, if they went through university, many universities had VAXs. It was superseded by VAX 11, which jumped it from a 16-bit machine to a 32-bit machine, and 32-bit addressing. So 16-bit machine, 32-bit addressing, so you could address a whole lot more memory. Its architecture. Now, there's a little bit of fascinating commentary in in this article on Wiki about the architecture. They comment here that it inspired the designs of the late 1970s microprocessors, including the x86 and the various iterations of x86, the 8088 and etc., the 4004, 8008, and then into the 8086, 8088, 8086, and then into all of the others, the 80386, the etc., etc., and the Motorola 68000. So that was their 16-bit machine that went on to the 6810, 6810, 68010, 68020, 68030, and the 68040. Now the 40, I actually did a course on the 40, so that was an interesting course. That was a 32-bit machine, but the interesting thing about it was a CISC processor. So that's a complex instruction set computer. It is 16-bit little endian, and all that means is the 16 bits are represented by the least significant bytes is the lower address byte versus the big endian machines, which was the least significant, was in the higher byte when you represent and move things around within the architecture. It's a register stack of R0 to R7. There are a whole lot of instructions around moving between registers, moving registers to memory, moving memory to other bits of memory. And the key thing here was it used a unibus type system where it pioneered direct memory access. So and this is where DMA controllers come in, direct memory access controllers, because the way that you interfaced to external devices was through banks of memory, and you would put things in particular memory positions, and that would then be sent out to the various I/O channels, etc., etc., etc. So everything was done through memory addressing, which meant if you could speed up the memory addressing, you could speed up the I/O. That was the downfall of this machine, because they sped it up and sped it up and sped it up until they got to the point where direct memory accessing and a unibus arrangement, they just could not make it any quicker. And so that was one of the downfalls of the machine. So there's a little statement in the wiki article that just talks about the fact that they got to that limit. They really got to that limit. It's an interrupt-driven machine. So this was another concept that was introduced in the PDP-11 from other machines, but there were 8 interrupt lines. For those who don't know about interrupt lines, what it enables programmers to do is write little routines that if they get a particular interrupt signal that comes in, so there's something that, and this can be coming in from an I/O channel, or it can be coming in from a memory trigger, or coming in from all sorts of things, it triggers the program counter to jump to a particular part of memory that then can run a routine, an interrupt routine, so an interrupt driven routine that does things, moves things around memories, resets things, does whatever it needs to do, and then it jumps, the program counter jumps back to where it was interrupted and continues. So you've got this ability to have real world and real time things interrupting the processing, and having that being processed and then continuing on with what it was processing. So it's a real programming concept, and there were 8 of these interrupt lines in a PDP-11, which were used for a variety of operations. The instruction set. Now I can show you some of the instruction set, because this wonderful programming manual is basically a workbook, and you can see You can see, let me open up to a random page, which is probably, and we go to, let's go to here. Okay, that's good. So there's a whole lot of things you need to work through, and I assume this assumes that you've actually got access to a PDP PDP-11, and I'll say you can even get access to a PDP-11 these days, and I'll hold that thought because I'll show you how you actually do that. But you can see here, you set R1 to a particular value, you move the low byte to R1, you clear all num, which is a register, again add R1 plus to all num, compare R1 and the high byte. I think that's the high byte. I think I'm right there. And then there is an instruction called BLOS going back to again. So this is a little loop here until it gets to a particular point, and then it halts and drops out of here. There are some settings here, which is the variable settings, which are all num is a word. So that's a 16-bit word. The low and the high word is set to particular values. So that could be this could be relating to it could relate to memory operations. So moving blocks of memory. It could be relating to moving data out to an I/O part of memory, which is then sent to a disk pack or a tape drive or something like that. But that is assembler level. So this is one step away from the actual opcodes. The little what they call the assembler. So what it does is take commands like this, and then it makes them into the opcodes that the machine uses. Now the opcodes there are 8 and 16-bit opcodes depending on the instruction that you use in here. It loads basically all of those into memory as opcodes. So these are numbers that represent particular opcodes, and then it goes through and you can run that program from one memory location to the end memory location, and it will execute those commands as you go through. So absolutely fascinating. And all come because I found this particular book, and I went, ooh, okay. So the contents of this particular book, it takes you through in a structured way, and I'll just binary and octal numbers. They don't introduce the concept of hexadecimal numbers in here, so it's interesting. Binary and octal numbers. I still have calculators that do the conversion from decimal, binary, and octal and hexadecimal numbers. Initialization of particular things in PDP-11. Branching commands, so where you jump around, you jump from one memory location to another within a program. What all of the registers are, there's push and pop stacks, so this is pushing and popping, so pushing things into particular memory locations, and those particular memory locations are to do with input, output, and disk drives and all sorts of things. They can be to do with machine control, program control, etc. Input and output, so how do you get things in and how do you get things out of the PDP-11? Little subroutines, so these are little bits of program that sit there and do particular things in a loop, or do it for a particular period of time or for a particular condition. Program interrupts, so how do you deal with interrupts when they occur, and then byte instructions. So it takes you through that in a structured way, and gives you little exercises to go on with. Now, in the front of here, the interesting thing is there is a bit of an advertising picture here. Let me zoom out a bit here. Digital introduces the PDP 1170, the system all other 11s have been leading up to. I love it. And the picture that Phil sent in was of the particular processor and the memory and storage units. These are 19-inch racks, or pretty close to 19-inch racks. So that gives you a bit of an idea of the size. You can see the terminals. There is a CRT terminal here, with a screen and a keyboard. And in fact, the VAXs went on. VT100 terminals, which became the standard for terminals, came out of DEC. These are teletype type terminals, so there's a keyboard and then there's 15-inch fanfold paper, which is what the program's printed onto, or the command that you're typing in here, and then you can run things and it would print out to the line printer. These are line printer type devices. So there you go. PDP-11s. I can't believe this. Now, the interesting thing, the other thing that it says in the in this wiki article, the programming languages that we used. Originally, it was the PAL-11, PAL-11. So that stood for Program Assembler Loader 11. So that enabled you to put things in with mnemonics, so literally write it in vague English, and then the PAL, or the Program Assembler Loader, would convert that to opcodes and then run it on the computer. They then came up with Macro 11, so this is what they call an assembly language. So you're getting closer and closer to English commands to do loads and moves and adds and subtracts and all of that sort of stuff, and that did the same thing. You then compiled it. When you compiled it, it transferred those commands into opcodes in the right sequence. It did some checks, etc., etc., and then it would allow you to run that program. And then the Unix assembler, which was called as the Unix assembler, was also used to program PDP-11s. And the interesting thing here was, one of the first versions of Unix was written and ran on a PDP-1120 in 1970. And you also had the forerunner to DOS, which was CP/M. I ran Z80 machines with CP/M and an S100 bus machine with CP/M, a Smoke Signal Broadcasting Corporation S100 bus machine. That was one of the first computers I ever was able to use, and then migrated and upgraded to a Z80, like a Super 80, Dick Smith Super 80, with 64 kilobytes of memory, and that was the bee's knees in the day. And then CP/M ended up becoming MS-DOS, and that's the entry of Microsoft, and the rest is history and all that sort of stuff. The last model of the PDP-11 lines were the single board PDP-1194s and the PDP-1193s, which were introduced in 1990. And when they say they're single board, literally they are a single board computer. Everything was on one board. And it came in a little sort of 2 or 3 rack unit high case, 19 inches wide, and that was the last of the PDPs that were ever created. A far cry from this sort of sized, taking up a room with disk packs and everything. Now, when I put the I mentioned you too can have one of these. There is a wonderful company, I think it's a German company, called Obsolescence Guaranteed. What a fantastic name. Obsolescence Guaranteed. Now, this particular person has created a PDP 8, a PDP 10 and a PDP 11, I think. It's something like... here we go. If I zoom over here, if I zoom... no, I didn't want to do that. Let's go back to here. Sorry, I'm just jumping around here. The PDP 8... the PDP 8... the PDP 11 and the PDP... what's that one? No, I can't get over there for some reason. Why can't I get over there? Oh, yes, I can. So the PDP 8, the PDP 10, and the PDP 11. What he's created is the Pi DP 8, 10, and 11. So this is all 3D printed. It has the very similar, very similar control panels to the PDP 11. And if I go back here, you can see down here, this is the PDP 1140 control panel. He's actually got a PDP 1170. So what you've got here is a whole lot of control switches. You can put in data, you can put in addresses. So you can actually put in at the opcode type level, so the binary type level. And there are a whole lot of control switches here which enable you to, I suspect, increase the program counter, decrease the program counter. There'll be clocking, there'll be all sorts of things in here, as well as your data and your address bus. So you can set all of these up so that you can load the data and the address in, and then there would be a load button. There are a whole lot of status LEDs up here which tell you what the machine's doing, what opcodes it's up to, what the count is, what the data bus and the address bus is telling you, so you can do a whole lot of decoding of your program. And then there's a whole lot of control, there's little control rotary switches here. Now, I understand that Andrew, let me just go back here, Andrew posted, oh, here we go. I can't find the citation link just now. Old New Scientist of IRC talks about a very early ANPR or automatic number plate recognition system using a PDP-11 in a porter cabin on the side of the motorway. I love it, Andrew. I love it. I love it. And hello to Bronson the Cat from Caboolture in Queensland. Bridge over the M1 with a video capture card. Well, there you go. And Warren, oh, well, now Warren's back in VK3. Oh, God, he gets about. I've never used a PDP-11, but I've seen them being covered by Asahi, Asahi Electric on YouTube. Now, Asahi Electric, for those who don't know, have a look at the website, because it's an absolute rabbit hole. Absolute rabbit hole. Asahi Electric is building a Valve computer right at the moment. And that Valve computer, it's all CNC PCBs and all sorts of things. So Asahi Electric is definite rabbit hole to go down there. The guy is just outstanding, absolutely outstanding. Now Andrew has also built, I think has built a Pi DP-8, which he showed a picture of it sitting on his shelf. So there we go. It should, okay. It should be clear from the above that the Pi DP owes its features to SimH, the emulation program fine-tuned over decades by Bob Supnik, Mark Pizzolato, and many collaborators. George Hope is the man behind the Blink and Bone variant of SimH that revives original PDP panels in museums and drives virtual panels. The PDP-11 is now added to that list of options. So it's just absolutely phenomenal. PDP-11. So you too can have your own PDP-11 run by a Raspberry Pi in the background. So absolutely fascinating. Now, when I put the PDP-11 on the Discord channel, what we ended up with was, if I go to here and then transition to here, Sean, VK7WTF, said, "Have I got a deal for you?" And he walked in with this box, which is an original digital box, so Digital Equipment Corporation box, and a whole pile of stuff. Let's go into what was in the box first. So this is a a hard disk that would have gone into a washing machine sized disk pack. So a hard disk hardware. This contains a platter, and if I very, very carefully, not that I think we're going to use this again, you can see inside of there is one platter which has the iron oxide on it, and it's all connected to a big spindle on the back which plugged into the disk pack. This went in the top of the disk pack, and the machine would have lifted the cover once everything was spinning right, and the head went in that way. And so I don't know what the storage is on this. Let me have a look. And in fact, if you knew the digital number on here, you could probably work this out. It's a DEC Pack 2200 BPI-12, and it's interesting because this particular disc contains a particular sportswear company's system disk backup, the backup for drive O, the system disk and programs, and the backup for orders and the general ledger. So there was obviously a PDP sitting there, and this was one of the discs that was on there, and this is original box that the disc actually came in. So, and these I suspect would have been worth an absolute fortune. So now the other things that Sean bought in was one of the tape drives. This is a tape. I'm not going to take the top off and unlock it because the tape's probably going to go everywhere. But this is quite a large reel, lots of storage, and you would load this onto you would unlock it, and then unlock. No, that's locked. I need to unlock it. There we go. And you take that off, and then you'd load that tape, and I'm not going to... That's what I mean. It gets out of control really quick. You can see it's quite wide tape. It's probably, I don't know, what's that, 7/8 or 5/8 of an inch tape. You would load that into a tape drive and then start the spool, etc., etc., and then start. There's no indication of what's on this particular tape drive, but anyway, and then it all gets locked away and then locked back up again so that it's protected. Now the other one was slightly more modern tape drive, and the interesting thing is this one does have a label on it. This is the McDonnell Douglas Release 7. Now McDonnell Douglas, that was a computer that I know the hospital used for quite a while, in fact a very long time. So this is one of their tapes, computer tape, 3M computer tape number 777. Same width as this one, so the 5/8 tape I think. Number 1.0.9.5 master 1096. So probably a bootloader or something to get things going again on the McDonnell Douglas patient information system. So absolutely fascinating. And the other thing he bought in, which is a blast from the past for me, because the smoke signal broadcasting S100 system that I was talking about earlier used 8-inch disk drives. Now this is double-sided. Woohoo! So this is a lot of storage, and it's controlled data, and you can see this is interesting. There's a little tab on here that you put on here which makes it read only. You can't write to the disk. So it's supplied by Memorex, which was one of the big memory companies. So that's 8 inches. Then there was a 5 1/4 inch. There was a 3.5 inch, etc., etc., etc. Got smaller and smaller, and the disk drives and the hard disk got bigger and bigger, and etc., etc. So absolutely fascinating. Absolutely fascinating. So let's get back to Okay. All right. So that's PDP 11s. Now, just let me go back here. Make sure there's no other comments. Who out there? Who out there operated? David. I remember my first computer was a Commodore 64. Yes, okay. Home computer, fantastic. Yes, I used a Commodore 64. Used a Commodore 20 before that, and used a Sinclair ZX81. So, and can I just say the keyboards on ZX81s were crap. So yes. Now McDonnell Douglas, like the US aircraft manufacturer, McDonnell Douglas. I think you might be right there, Lionel. I'm not quite sure, but I would not be surprised if McDonnell Douglas was also producing computers. The double frequency non-return to zero NRZ recording methods used on these drives can store up to 2 million bits of online data in the RK05 and RK05J. So RK05K is what we've got, and up to 5 million bits in the RK05F series. So we're somewhere in the middle of that. So somewhere between 2 million and 5 million bits. So that's a pretty reasonable amount. And Google says, yes, one and the same. Interesting. There you go. Excellent, Lionel. See, I've got my army of researchers out there. I love it. I love it. Okay. All right. PDP 11s. We'll put PDP 11s to bed right at the moment. I just wanted to give you a very, very quick update for our. This will be for our REAST members. REAST and WICEN. Now, WICEN, for those people who are on the stream, WICEN is the Wireless Institute Civil Emergency Network. That is our emergency communications arm in the Wireless Institute in Australia. WICEN in Tasmania has made the decision to merge with REAST, with the Radio and Electronics Association of Southern Tasmania, and just got a little bit of an update because there was agreement by WICEN, there was agreement by REAST, and the next steps that we took was to get together a merger agreement, which is what we do with assets and what we do with various bits and pieces to get the merger to happen. That merger agreement's all been put together, been checked by the legal beagles, and has been signed. So there is a bit of a milestone that has been signed. The next step is to get the WICEN members together and to basically wind up WICEN. And WICEN becomes part of REAST and a subcommittee of REAST. So that's the update around WICEN and REAST. Now, we had, a couple of weeks ago, we had a fantastic presentation, and I will post in the chat comments, in the video comments, a link to that presentation by Mars Buttfield-Addison. Now, Mars, I started to do a little bit more reading about Mars, and her partner Paris have become members of the club, which is fantastic. Mars is a fantastic science communicator. She's a computer scientist, and was Tasmania's STEM Communicator of the Year in 2023. These are the things I found out. Worked in software development, data science, machine learning, and high performance computing. Has an absolute love for the teaching of technology, and for those people who have done anything in the ICT area, they would have come across the O'Reilly books. Now, the O'Reilly books are the Bibles on particular programs, on particular things that you do on the internet, applications, all sorts of things. There is just about an O'Reilly book for everything. Now, both Mars and Paris are authors of O'Reilly books, quite a number of O'Reilly books. So if you come across Mars Buttfield-Addison, or Paris, Buttfield-Addison on those Riley books. That's. Don't be surprised. Don't be surprised at all. But I also, and I neglected to mention when I introduced Mars, which my bad. Mars was actually is a science superstar of STEM, or science, technology, engineering and maths. Now, the Superstar of STEM is an initiative of Science and Technology Australia, funded by the Australian Government's Department of Industry, Science and Resources. Through a highly competitive selection process, the program selects 60 women and non-binary STEM experts and gives them training, confidence, networks and experience to become sought-after media communicators as experts in their field. And Mars is one of those superstars of STEM. And I'm a big listener to the ABC Science Show every Saturday. And Robin Williams absolutely bangs on about the superstars of STEM. And so I'm looking forward to when Robin actually interviews Mars. So there you go. So that was a little bit, and I will post Mars's website, which is absolutely fantastic, in the video comments as well. So definitely worth a look. Now, to finish off, I will move our PDP storage and give you an update. On this is the baby magnetic loop that I have been working on. I gave you a bit of a view of it a short while ago in its undressed form, and so this is in it's got its housing around it. It also has the vacuum capacitor drive, and I'll show you that in a sec. But it's in its weatherproof cover. There is a cover to go on the top. You can see the top of the vacuum capacitor in there, and it's all of the structural strength. There is a N-type connector that sticks out the side here. There is also down here there is a connector which is the drive for the vacuum capacitor motor. This is a 6 to 15 meter loop, so it covers 6 meters all the way to about 56 megs, and then all the way down to about 20 megs. Which gives me 15 meters and also 10 meters as well, in a directional magnetic loop antenna that's capable of putting 100 watts through it. So what I was going to do was show you. I haven't. Let me just wrangle that off. Oops, sorry about that. That I have to do it with the top one. So let me turn this over, and I take that cover off. I made this a little bit different to the other one that I put together, purely because of its size. Now what I can do is turn over to that one. Great. So what I can do is, let's zoom in here a little bit, and so you can see at the top vacuum capacitor, which is 4 to 100 puff picofarads. It has copper plates which are silver soldered with 46% silver solder, which is the highest level of silver solder that you can get. To get what you're trying to get is your ohmic resistance down to the characteristic of the heliax, which is what I've been able to do. It is then mounted. There's a bit of a plastic, a Teflon strengthening arrangement here, which basically keeps all of this in place without putting any strain on the vacuum capacitor. There is a connecting line with a bit of fiberglass rod that goes, and I'll just, all the way down to, you can see there's the coupling loop. That is a bit of a smaller heliax, which literally connects straight into the, there's an end type with a barrel in there, and it goes all the way down to the, now I showed this a little bit a while ago. I showed this a couple of weeks ago. This is the motor drive for the vacuum capacitor. Now I needed a motor drive that gave me 22 turns, because 22 turns gives me from one end of the vacuum capacitor, so the 4 picofarads through until the 100 picofarads. And I've also put limit switches on this. If I turn this over, you can see there are micro switches on each end and a little Teflon bumper that moves along, and so I don't overshoot the vacuum capacitor. And that's connected up to, and this little one here gives us a 5 RPM, so 5 revs per minute, so pretty slow. There's a little 12-volt motor, there's a little gearbox, and it goes into that threaded rod. So so that's the drive for the mechanism, and that's connected up to the magnetic loop tuner. So the magnetic loop tuner then basically has control of this motor, and it does a scan of the loop, and the that loop then does a scan of the loop, finds out what frequency it's resonant at, finds out what frequency you want it to be resonant at, and then moves that motor to give you that resonance. So anyway, this is about to be pressed into service. Six, which is good, because there are some 10-meter openings that are still happening down here. I think 6 meters has well and truly disappeared off the face of the earth, but 6 meters is still well and truly happening. And I know that because on the John Moyle Memorial Field Day on the weekend, I went to 10 meters, and the first station that I heard was a Russian station. An R0 station, and I just went, wow, okay, that's pretty impressive. So yeah, there was an R0 station, some EA stations, and some other stations that were coming out of Europe, as if they were sitting next to me. So 10 meters was well and truly open on the weekend, and was the place to be for the contest. So and I was only running 100 watts and a dipole, so linked dipole. So there you go. Anyway, that's now we'll just finish off. We're right on time. I love it. Space weather report. Now we do have a HF fade out warning, which is if comms difficult experience, try a high frequency band for the 20th, 21 and 22nd of March. We've got R1, R2 all probable, so more than likely HF comms fade out. So go up in frequency if you're having trouble at lower frequencies. Bit of a heads up, our coming presentation nights. First Wednesday night in April, which is April the 3rd, is Peter Picorni, VK2 EMR, and I was in a meeting with Peter last night, so I confirmed that he's still okay for this particular talk, which is great. He's doing a very humorous talk on the history of UTC and the leap second, and it is might sound a really dry subject, but Peter absolutely had the house coming down and laughing their head off during this presentation when I last saw it a couple of years ago. So he's updated it apparently for the other leap seconds and bits and pieces. And then on the first Wednesday night, which is May the 1st, May Day, I'm giving a talk on Frederick or Pop Medhurst, who was A7AH, who's a Tasmanian wireless pioneer. If you were a receiver of AR magazine from the WIA, you will have noticed a article about Pop Medhurst in that particular magazine in the last edition. So he did huge amounts of things, both in telegraphy and also in wireless, early wireless. This is Spark Wireless, one of the first to talk to the British Navy when they accompanied the Duke and Duchess of York to the opening of the first federal parliament in Australia. So interesting. Anyway, lots of stories about him and lots of history about him. So that's our presentation for tonight. I hope you've got something out of that, and please send me your PDP-11 anecdotes. And I absolutely love it. Bit of history about computing heritage. Absolutely love it. Anyway, 73. We'll catch you next time, and with another fascinating show. Catch you around.